The statistical process control is application of statistical techniques in quality control. We measure values and we expect those measurements to be in a range, to be called conforming to expectations. This could be weight of the product, size, dimensions, time, count of the problems or potential problems we expect, proportion defective of large samples, or other things. There are two types of measurements we do in quality control. We might measure variables. Variables are values that we can measure, such as weight, length, volume, or time, with standard scales. The second group is attributes. These are the values that we can count. For example, the number of scratches or blemishes on the paint of a car or a room. We don't measure them by size, we just count them. But the weight of a box or measuring the length of a bar, these are variables. So there's a difference between variables and attributes, and there are different distributions these measurements follow, and there are different types of quality charts. Typically for more complex performance, or when the measurements are difficult to do for variables, we use attributes. Sampling rules. Sampling must be random. So we follow intervals of time or quantity, for example, every 15 minutes, every hour, or every 100 units out of the production. Distance, sampling the pavement every 500 yards, etc. Individual observations vary. Typically, we take samples in quantity, we average the measurements, and use those averages when we're going to make charts and control the process. Large sample sizes tend to decrease variation. If you look at the range and standard deviation of the samples, larger sample size shows a smaller standard deviation. It's less dispersed. Large sample sizes are more likely to detect shifts. We've seen this in an example before. And expected value of the sample mean is a number we expect to be the mean of the population. When making a control chart, we have basic elements. The first element is a central line, and that central line is the average of all samples, or a target value we expect the samples to follow. There are two limits, upper and lower. Upper control limit and lower control limit. We develop these two limits based on the distance from the center, or the mean of the sample. So the control limits are the average or the center line plus minus a given number of standard errors. That z-score could be 2 or 3, and then the standard error, we calculate that as standard deviation divided by the sample size if we use the samples. So after establishing the upper and lower control limits, for example, we have a number of samples. Those samples have different distributions, but the mean of the sample, follow the mean of the samples and see that all those means are between the upper and lower control limits. We call the process in control. If we observe that one of those sample means is beyond the control limits, then we call the process out of control. It's not just that sample out of control, that process is out of control, because what happened for this sample could be repeated. We have to find the source of the problem and the cause of the deviation. Control charts for variables are range chart and average chart, or as we call them, R chart and X bar chart. We need to monitor the mean and variability of the process, because when we are measuring a variable, we can find out what the range is, the difference between the minimum and maximum of each sample, and what's the average. So we will check both using two charts. If we use large samples and the standard deviation of the process is known, we use the base formula. Upper control limit is the overall average plus 3 standard deviations, or if we use a different number of z-scores, 2 standard deviations, and of course this is the standard deviation adjustment, standard error, dividing the standard deviation of the sample by square root of the sample size, and lower control limit is the mean minus 3 standard errors. In case we have small samples, or we don't know the standard deviation of the population, there are standard tables we use to find out the constants that replace the standard deviation. In this case, the constant a sub 2, for example, we find from the standard tables. Upper control limit of average chart or X bar chart is the overall average plus that constant times the average range, R bar, and similar formula for the lower control limit. Here we can see a partial screenshot of a standard table from ASTM manual on quality control of materials, and two constants we can find for upper and lower control limit of range chart based on the sample size. Here R bar is the average of the ranges measured from the previous samples, and D3 and D4 are constants we find from the table. In this example, we have 5 samples, and each sample has 4 observations. So the sample size is 4. The standard deviation of the population is not known, so we use the standard table. First step, calculate the range and average of each sample. Range is the difference of minimum and maximum of observations. So I get the difference of the maximum of 4 observations and the minimum. As for all samples and average. With the average of the range and average of averages, X double bar. For the range chart, we have a table here prepared. All those ranges for samples are copied here in one column. We need to retrieve 2 numbers, D3 and D4, for the lower and upper control limits of range chart. We go to the table. For the sample size of 4, we'll find that D3 is 0 and D4 is 2.282. So we plug them into these 2 formulas. Lower control limit, the D3 is 0, so that will be 0. Upper control limit, D4, which is 2.282 times the average range, 0.0941. The average range is also 0.0941 in one column. To create the 3 straight lines, the average line, upper and lower control limit, we have to copy these numbers down into the columns. Then I will use this entire table to generate the chart. A line chart. So this will be my R chart, the upper and lower control limits, the middle line, and the samples. The ranges, we plot them here. They are between the upper and lower control limits, so we have no serious problem with the range. In case you want to show these points as a point not connected, you can select that line in Excel, right click, change series, chart type, and open this box, change from line to scatter. And you will see 5 points. So that's for the R chart. For the average chart or X bar chart, the same way we copy all averages into one column, average of averages in one column, and upper lower control limits. A2 from the standard table for the sample size of 4 is 0.729. So multiplying that number by the average range and then adding to the formula with overall average, We get 3 numbers here, and we can copy them down into the column and use this table to generate the average chart. Insert a line chart. Right click on that line, change series chart type, change it to scatter, and we can see that the average is out of control. One of the samples is too light. That's a special cause. We have to find the source of the problem. In my next example, the target value is known. The target should be 1, and the standard deviation of the population is also known, 0.019. We start the same way, finding the range and average for each one of those samples. For the average of averages, since the target is known, we are going to measure the performance against a fixed target. So we just put down 1. For the average range, we calculate it. For the range chart, we use the same way. Find the fixed numbers, the constants, D3 and D4 based on the sample size of 4, and plug them in. Then we'll copy the numbers into 3 columns to generate the upper-lower control limits and the central line. And then insert a line chart based on this table. For the average chart, the average is fixed, is known, and it's 1. Upper-lower control limit, if you develop a chart based on 3 standard deviations, that will be the mean or target value 1 plus minus 3 standard deviations. So we use 1 plus 3 standard errors, dividing the standard deviation by the square root of the sample size, which is 4. We use the formula for the lower control limit as well. Same thing, mean minus 3 standard errors. And insert a line chart here. Based on this line chart, we can see that 4 of those observations are beyond the control limits. Now we copy this data into JMP. First thing we need to do is putting all those samples together in one column. And of course, one column should be marking them as belonging to each sample. So we stack these 5 columns. Go to tables and stack. The column of data is the data or measurement. The column label will be sample. Go to Analyze, Quality and Process, Control Chart Builder. The variable we're measuring goes to Y always. So the data stacked, all those observations, goes to Y area, and sample is the subgrouping value. We always have a subgroup, so we drop it into the horizontal axis, and this will be the average chart and the range chart. Here we can see short variables from this drop down. There's also short attributes. Since we dropped in a numerical value, the column was continuous into the Y area. The system automatically decides that this is a variable chart. So It's a variable chart pair of X bar and R chart. On the right side, we can see the average, upper and lower control limits for two charts, for the average chart and the range chart. If you compare the lower and upper control limits and the average, these are the same numbers we got in Excel. One of the things we can do here, right click on the chart, warnings, test beyond limits. And we can see if there's any point beyond the control limits, there's a red circle around it. So that's one of the easy ways to find out if a point is out of control or not. If that's too close to one of those upper or lower control limits, we're not sure it's beyond the limit or not. For the range chart, we have no problem. All points are between the upper or lower control limits. I will introduce two types of control charts for attributes. First is P-chart, based on a binomial experiment. The binomial experiment is a sequence of identical trials. Each trial has two possible outcomes, call them success and failure, and probability of success does not change from trial to trial. Those trials are independent. This is a good fit to a large sample we take and then check the observations, check the units within that sample, if they are conforming to the standard or not. If they're not, they're defective. A useful number we can get here is proportions of defective elements, and those proportions follow a binomial distribution. So a P-chart is a chart used for controlling the proportion of defective services or products that are generated by a process. Standard deviation of a binomial distribution has a formula. That's a square root of a ratio, and that ratio is based on the P-bar. That P-bar is the central line of the chart, and that's the average proportion defective. N is in this formula is the sample size, and the basic formula for upper lower control limits is that P-bar, the average, plus minus 3 standard deviations, or a different number of standard deviations if we choose to. We have another chart for attributes, C-chart, which is based on Poisson distribution, which is a type of discrete distribution. Here we are talking about the counts of a number of events in an interval. Could be the count of the number of problems along a timeline or any other line of highway or a line of customers, how many problems we have in the line of customers or in any other queue. It's based on a Poisson distribution. A main characteristic of the C-chart is that it controls a process by counting the number of defects on each unit. So for example, if we take a sample, electronic device or car or any other product, and count the number of problems on each unit. For example, say 2 problems here, 11 problems on the next item, and so on. Finding the problem is an event. So these numbers follow a Poisson distribution. In Poisson distribution, the mean of the distribution is the variance. So the standard deviation of the distribution is the square root of the average. The base formula for upper lower control limits is still the same, average plus minus 3 standard deviations. So we use the same formula to develop the upper lower control limits. Well, before going to the examples, this is important to know how to select your chart. First question you have to ask is, what is being measured? Is it a variable? Is it a length, weight, time, or anything else? Can you have a meaningful range of measurements for each sample and the average of the sample? Is it a standard scale of measurement? That's the sign of a variable chart. Then you need to make X bar and R chart, average and range chart. What you're measuring is an attribute, and that attribute, there are 2 types of attributes. If you're counting the number of defects on each unit, you're sampling and then counting the number of problems. That's a C chart. You're following a Poisson distribution. The other type of the attribute chart is P chart. If you're looking at typically large samples and you have the criteria accept or reject, you're not tracking the type of the problems, you're not tracking the number of the problems on each unit. You're just recording how many units are defective out of a sample. So that's reject or accept, failure or success, a binomial process. And that's the sign of a P chart. Now we go back to the Excel file we downloaded from the module and look at the P chart tab. These are 12 samples taken. The sample size is 2500, one sample per month, and these are the number of wrong account numbers, 15 for January, 12 for February, and so on. This is a binomial process because we just know that this number of samples were defective. We don't have any other information. We don't have the count of problems. We just know that out of 2500, we have this many samples defective. So the first step is calculating the proportion defective. And what's the proportion defective? The ratio of the defective over 2500. Formula in these cells, just divide the number defective by 2500. We do that for all samples. The average of proportion defective is the average of all these numbers. And the formula of the standard deviation. Plugging in the formula, P bar times 1 minus P bar, dividing by the sample size and taking the square root. So the upper and lower control limits will be the average plus minus 3 standard deviations. So these are the upper lower control limits. The same way we developed the control charts for X bar and R. Do that here as well. We have a table copying all those proportion defectives, the average, middle line, and upper lower control limits. We copy these 3 numbers into the columns to establish the lines. And then insert a line chart over this table. We can see that in 1 month here, month 7, the process shows too many errors. It's beyond the upper control limits. So we can call the process out of control. Next example, we go to C chart example, C chart tab in Excel file, measuring the number of blemishes on a roll of paper. We have 6 samples, 16, 21, 17, 22, 24, and 5. So we can calculate the average. In any case, the average could be given. For example, a target value. We're going to develop control charts based on 2 signals. Standard deviation is the square root of the average. So upper lower control limits will be the average plus minus 2 standard deviations. The center line, upper lower control limits, you can copy them into the table. And then we'll insert a line chart over this table. You can see that for most parts the observations are between the control lines. Last observation is below the lower control limit. And that's a good thing. It means for the last observation, it's much less than our expectation because we are following the blemishes problems. And this is a point for benchmarking what we did that was good ended up with such a low count of blemishes. Now I will go to JMP and show how we can do control charts for attributes on JMP. Under Help menu, Sample Data Library, there's a folder for quality control. Open this file, Bottle Tops. Here we have 2,700 observations. Samples taken are 54. Each sample is 50 observations. For each one of those bottle tops checked, there's a mark here. Does it conform or non-conform? So the number of non-conform determines proportion defective in each sample. Everything else is formulated in the software. So what we do here is starting the control chart under Analyze Quality and Process Control Chart Builder. Since we are tracking the conform and non-conform out of a large sample size, we have to decide this is a P chart. The variable we are measuring, conforming, should be into Y. And we have to subgroup by samples. Since we dropped in a non-numeric variable into Y, Chart attribute is already selected. For the P chart, we have to change this drop-down statistic to proportion. Distribution is already binomial. There are two options here, proportion and count. Proportion is for P chart, count for C chart. Two options here for the limits, sigma, binomial for P chart, and Poisson for C chart. So the combination of proportion and binomial. And on top of the chart, we can see P chart. Process is obviously out of control. You can see the observations here. There's a variable here, phase. It means people did something at some point that made different phases. Phase should be on top in this area. If you do have a phase, the variable may not be called phase, but then differentiate between 2 or 3 different timelines. Drop the phase here. It will separate phase 1 and 2. And as you see, it will separate the charts. We have 2 different charts with different upper lower control limits and averages. And we can compare them. In phase 2, the process improved. We have different signs for that. The green line, the middle line, which presents the proportion defective, is lower. There's a drop in proportion defective. There's less variation. The upper lower control limits are closer in the second chart in phase 2 compared to the first chart. That's a sign of more consistency as well. And there are no observations beyond the control limit. If you're not sure about this point here, very close to the line, right click, warnings, test beyond limits. There is no red circle around it, so it's not beyond the control limit. While these 3 points here, we can see the red circles around them. Now open this file, Fabric. We have bolt number, which is our sample, and the count of flaws. We are counting the number of problems on each unit. It's count. It's on each unit. A clear sign of looking for an event, detecting a flaw. That's a Poisson distribution, and that's a sign of a C chart. So when we go to Analyze and Quality and Process, Control Chart Builder, the variable that measures the flaws or problems goes to Y. Since we dropped in a continuous variable, the system automatically builds a pair of X bar and R chart, which is not the type of chart we need. We need to change from variables to attributes. And we need to drop the bolt down here, so that we can subgroup by bold. Just make sure the pair of count and Poisson are selected, and on top you can see the C chart. The upper lower control limits and the average are on the right side, and the process clearly is out of control. Open washers file. This is a different type of P chart. The P chart is the same, but the configuration of the file is different. Here we do have the lot number, and we do have the lot size. Lot size 2 is a simulation of if we do have different lot sizes, how the chart will look like. And then the number of defective washers in each lot of 400. We're going to work with 400. Well, first of all, the number of defective, we don't have the count of problems on each washer. We don't have the type of the problem. We just know that the washer was defective. 1 in 400 in lot number 1, 3 in 400 lot number 2, etc. So we just have the proportion defective. This should be a P chart. In control chart, number of defective goes to Y. Since this is a number, the system builds the pair of X bar and R chart. We have to change this to attribute first here. We know that's a P chart, so we need to set the combination of proportion and binomial. We have to subgroup by lot number. Here we do have the average line, but we don't have the upper lower control limits because we're missing the lot size. There's a box here. We do have the lot size and trials, number of trials, and that's the lot size. We drop the lot size into this. And now we have the upper lower control limits. Now open this file, diameter, 240 observations, day of sampling, diameter of the product measured, operator, machine, and phase. We can look at the control chart, which is pair of X bar and R chart. Y X bar and R chart, we are measuring diameter. That's similar to length. So standard scale, we can measure the average and range of each sample. Each sample, since we do have the days, we can subgroup by day. So diameter automatically makes a pair of X bar and R chart, subgroup by day. We always subgroup by day. Or another factor, if for example we do have hours and it's specifically mentioned, then we subgroup by that factor. The process is out of control. Both the average and the range, we can see for the range chart there are points beyond the control limit. Now if I'm going to look at the performance of individual operators or machines, I do not build the chart based on an operator. I don't subgroup by operator because that will accumulate all the samples of that operator or machine into one point. We keep the same chart, filter for different machines or operators. For example, if I add a local data filter and add machine, for the 3 machines, I can select each one of those machines and filter for that machine. See what's the performance of the machine. Or clear the filter, do it for operator. You can also drop the phase in and see what happened in phase 2. Phase 2 improved the performance. The first sign of improvement is that the upper lower control limits are closer. The difference of upper lower control limits are closer the gap is closer comparing to phase 1. That means the observations are more consistent, are more concentrated around the mean. For the range, phase 2 range, the average range is lower. That's clearly a sign of improvement. And the gap between upper and lower control limits is smaller comparing to phase 1. So that's overall improvement in phase 2.